things. Hello, everybody. I am Jeff Lawson, the CEO and co-founder of Inertia. Prior to this, co-founder and CEO of Twilio for 14 years. But this is my new company. It is called Inertia. And we are the commercial fusion energy company. Now, if you know anything about fusion energy, you know that sounds kind of like saying like I'm a unicorn salesman or maybe here by my warp drive engine. But that is because fusion energy has been the thing of science fiction. It has been a dream of humanity for almost 100 years since it was first hypothesized. Because fusion energy is the holy grail of energy. It is safe, it is clean, it is cheap, and it is abundant. The only question has been, will it ever work? The basics of fusion energy are this. You take isotopes of hydrogen, usually deuterium and tritium, and if you bring them together in certain conditions of temperature and pressure, hundreds of millions of degrees, you can get those atoms to fuse into a helium atom, giving off a ton of energy. Now, for 75 years, people have built hundreds of machines attempting to do this. Billions of dollars have been spent trying to create a system where more energy is created than it takes to create those conditions, and no one has ever made it work until December of 2022. That is when, over in Livermore, about 60 miles east of here, east, I don't know where I'm pointing, an experiment that they've been working on for 60 years, and after $30 billion of investment, finally achieved this amazing milestone for humanity called ignition. They got out more energy than they put into the experiment. Is the first time ever. Now, the way this experiment works is they've got this tiny little ball, the size of a pea, full of deuterium and tritium, and they hit that tiny little ball of fuel with the world's largest laser. And if you hit it just right from all sides at exactly the same time, you implode that tiny ball of fuel, and you create those conditions of hundreds of millions of degrees, and they got fusion. In fact, they got more energy out than hit the target. Now, they've not just done this experiment once, they've now done it many times, and they've increased the yield now multiple times over. So this is a proven experiment at this point. Now, the thing about this experiment is it's science. They collect a bunch of data from it. They're not actually here to make energy. So in order to make energy, you don't do the experiment once and collect a bunch of data and call it a day, which is what they do now. You actually do it repeatedly. So you have to do it at 10 hertz, 10 times a second. You hit one of these targets and release a bunch of fuel. And so there's a big scale up that we have to do in order to take this out of the lab and bring it into the realm of commercial energy. So we have a very simple strategy to do that. Number one, don't mess up the science. This was very expensive and took a really long time to prove, so don't wander out of the realm of known science. Number two, when you have choices in performing the scale-up, always pick engineering risk or economic risk. Never wander back into the realm of scientific risk. And number three, optimize anything later. Just get it working. That's the first step. All right, let me tell you a little bit of how we're going to do it. The first two things you need to know, the laser and the target, these are the two main parts of the system. The laser is this giant machine. It is 2 megajoules of energy on every blast. It is huge. It is incredibly inefficient. It is always breaking, and it is fragile. So we need to build one better than that. They can only shoot it once a day, and at full energy once every other month. The target is this tiny little perfect ball of fuel. They are made by hand. They make about a dozen of them a year. We need to shoot them 10 times a second, so we need to make 1 million a day. Very different scale of operation. So this is how we do it. We have a very simple plan of how we're going to do it. First step, start with science that works. I cannot overestimate this enough. Second, build the world's most powerful laser. Our laser is going to be 1 million times more powerful than the laser they have over at Lawrence Livermore. It is going to be 20 times more efficient, and it is going to be much more compact. The unit cell will fit in a shipping container, unlike the one they have over there, which is 3 football fields long. Next, we need to mass manufacture these fuel targets. So like I said, we need to make a factory operation out of this. We need to make them about 1 million a day and automate every step of this process. And last, we need to put these things together into a gigawatt scale power plant. That is enough power to power 1 million homes. That is the utility scale of this power plant. So we have a 5-phase plan for how we're executing on this. We're in the middle of phase 3 right now, which is doing engineering and design validation of our manufacturing plans. When we're done with this, we're going to go build our manufacturing prototype of that first laser cell and of our first manufacturing line for these fusion targets. When we're done with that, then we're going to go scale up about 1,000x from there and go build the first of a kind power plant. We are hiring a lot of engineers to make this possible. I imagine most of you are computer engineers, but we are hiring mechanical engineers, optical engineers, high-power laser engineers, systems engineers, mechanical engineers, I don't know, every kind of engineer you can imagine. So if you have an engineering in your title somewhere, we probably need you. So go to inertia.com/jobs, and this is how we are going to produce star power for life. We'd love for you to join us. Thank you very much, everybody.